is really focused on stability. Specifically, we're going to be focused on carbocation stability, and we'll talk a little bit about carbanion radical stability probably. Before we, let's see. I'm going to come back to this introduction. Let's look at this words right here. Carbocations and carbanions are more or less stable based on their substitution. And then we go into some definitions. Tired. Okay, but this is an exciting lecture. This is important. This comes up over and over. So a primary carbon is a carbon that's bound to one other carbon. Okay, so let me draw an example of that. That's horrible. Let's try that again. Okay, so this carbon right here would be considered primary because it's only connected to one other carbon. Okay. Secondary carbon, a carbon that is bound to two other carbons. All right, so this carbon right here is considered secondary because if you count, it's bonded to two other carbons. Okay. All right, a tertiary carbon is a carbon that is bonded to three other carbons. I haven't drawn an example of that. Man, I'm yawning a lot. I'm just drawing a crazy molecule here to use as an example. Okay, so tertiary carbon, this is an example of a tertiary carbon as well as this. This one up here is pretty ugly because notice they are bonded to three other carbons. So this one's bonded to 1, 2, 3 carbons, so it's tertiary. Same thing up here. This one's bonded to 1, 2, 3 carbons, so it's tertiary. Okay? All right. And then a quaternary carbon is a carbon that's bonded to 4 other carbons. So this is an example of a quaternary carbon because it's bonded to 1, 2, 3, 4 other carbons. Okay? So let's go backwards now and look at why do we care about stability? Well, we really care about stability because in most of the questions you have in organic chemistry, the reasoning that something occurs a certain way or whether it occurs or doesn't occur really comes down to stability. Is this a stable enough product for us to actually get it? Why does this mechanism occur and not this mechanism? Well, because this mechanism, we get a more stable intermediate. And so stability is very important for organic chemistry. As a reminder, molecules, they're lazy, they want to be stable. They don't want to do things that bring them at a higher energy level. So they like to stay low energy, and usually low energy means more stable. Okie dokie. So fill the correct substitution of each of the following elements. Okay, so what they mean by substitution is is this primary, secondary, or tertiary, or quaternary, right? Now, when you are talking about a carbon, you say, oh, this is secondary because this carbon is bonded to 2 other carbons. But when it comes to hydrogens, halogens, and hydroxy groups and all of those things, let's focus on hydrogens and halogens. How many bonds does a hydrogen make? 1. How many bonds do halogens usually make? 1. So if we use the same definition for hydrogens and halogens that we use for carbons, we would always get the same answer. So what do I mean? So let me draw an example here. So here's a hydrogen. This hydrogen, okay, is it primary, secondary, or tertiary? Some of you might say, oh, it's primary because it's connected to only one carbon. But if that's how we treated hydrogens and halogens, then all hydrogens and halogens would just be primary because they're always bonded to just one carbon. Okay, so when we're talking about hydrogens and halogens, we are actually going to associate their substitution based on the substitution of the carbon that they are bonded to, okay? So this hydrogen is not primary because it's attached to one carbon. No, in fact, it's actually secondary. And here's how you would do this. You'd say, okay, here's my hydrogen, here's the carbon that it's bonded to, and now I'm going to ask myself, what substitution is that carbon? Because that substitution will therefore describe the hydrogens that is bonded to that carbon. So this carbon is connected to two other carbons, so it's secondary. So that means because this carbon is secondary, I would describe this hydrogen as a secondary hydrogen. Same goes for halogens. So if I put a halogen here, like a chlorine, I would say, oh, this chlorine is primary, in a primary position, because it is bonded to a carbon that is primary. Okay? So I think that's pretty much it. And the same goes for hydroxy groups as well, right? Hydroxy groups, you don't look at the hydroxy group to determine substitution. You look at the carbon the hydroxy group is bonded to. All right. So let's answer these questions. So let's start with the carbons first. So what substitution is this carbon? Well, you say, okay, how many carbons is it bonded to? 1, 2, 3. So it's tertiary. All right, what about this carbon? How many carbons is this carbon bonded to? 1. So it's primary. Now we're going to look at the hydroxy groups and the halogens. So looking at this halogen, what's its substitution? Well, first we look at the carbon that it's bonded to and we figure out the substitution of that carbon. So this carbon is 1, 2, it's secondary, which means the halogen, the hydroxy group is also a secondary hydroxy group. Now let's look at the other hydroxy group. So this hydroxy group is bonded to this carbon, and this carbon is 1, 2, 3, tertiary, which means that this hydroxy group is a tertiary hydroxy group. And looking at this chlorine over here, let's look at the carbon that it's bonded to. The carbon that it's bonded to is 1, primary, which means this halogen is described as a primary halogen. Okay, so now that we can identify substitution either on a carbon or a hydrogen or a halogen or a hydroxy group, things like that, now let's look at how substitution affects stability trends.